Okay, we are comparing the thermal loads that we can get in this tool and the thermal loads that we had in the Revit report here. So if in different spaces, we add up this total, we are working with heating loads. So we add up the heating loads and we end up having the total heating load of the building. But in Revit, we can select the location, and this location, Revit has a database with indoor and outdoor temperatures of this location. Perfect. In this tool, it's more simple. So here we select the comfort temperature inside is always 70. So this is, yeah, we can say that it's always 70. But the outdoor temperature, what we are doing here, we are selecting the coldest day or the coldest temperature in winter that we can have. So we can select only one temperature. Revit runs this analysis millions of times a year, and then to select the maximum heating load, it selects the coldest day, or the day in which those heating loads are the maximum heating loads. And when is it? Well, we have here this. So Revit has selected January the 21st at midnight. It makes sense that probably the coldest day it's January the 21st. And what is the coldest temperature that Revit has selected? It's a negative 2.9 Fahrenheit. You see, this is the dry bulb temperature. So this is negative 2.9 Fahrenheit. Okay. And then the temperature, the dry bulb temperature indoors, it's 70 Fahrenheit. If it's not 70, it will be 69 or 71. And then the relative humidity is 29.8. The indoor relative humidity. We don't have information about the outdoor relative humidity, but we have the humidity ratio and we have the wet bulb temperature. Okay, so so this is outside and this is inside. This is the zone. So we have 70 Fahrenheit and 29.8. Well, so Revit analyzing the whole year. The maximum heating load is on January the 21st, and these are the temperatures that Revit has taken for that specific value. Okay, so if we want to compare this, we should type here a negative 2.9. Okay, so that will be the coldest day that Revit has found in that database. Good, so we have information. If we want, we have indoor relative humidity, it's been 29.8. So do we have indoor relative humidity? We do, so we can type here 29.8. And Revit doesn't give us the outdoor relative humidity. We have dry bulb and wet bulb. When the temperature is too cold, the dry bulb and wet bulb temperature is the same, but we have the humidity ratio. So where can we find the outdoor relative humidity with the temperature and the humidity ratio? If a long time ago, like 2 months ago, we did this psychrometric chart online, and we had this fly carpet, whatever. So remember that here we have to set English units, reset inputs, and then click submit. And here we have the inputs. The dry bulb temperature is negative 2.9. And here we have to select the humidity ratio which we don't have. Okay, so this we have here the specific humidity in pounds divided by kilopounds. So what are the units in Revit? It's pounds divided by pounds. So if we want to, if we have to do this in pounds divided by kilopounds, we have to multiply by 1,000. It's difficult. Okay, well, it's difficult. It's not. So we need to know what we are doing, because if this is 0.0007 times 1,000, I don't want to make a mistake. So it's 0.7. Okay, yeah. So it's 0.7. So here on this chart, in this specific humidity, we have to type 0.7. So if we do this, we click here and we click submit. Okay, we don't see this because here we only have up to 20 Fahrenheit. Okay, so this is -2 Fahrenheit. So this is out of the range of this, but we have the relative humidity. The relative humidity is 103. It's impossible. Okay, so the relative humidity, it's very high. 103. It's impossible because the maximum relative humidity will be 100. So when this is 100, we can type that the relative humidity outdoors, it's 100. So it's a very cold day and very humid. Maybe it's snowing or something like that. So when it's raining or it's snowing outside, the relative humidity can be very close to 100. Okay, so with this, we have the conditions that Revit has taken. Okay, but it's not very straightforward. So there's we won't find the answer. Okay, what's the relative humidity? What's the temperature? So in Revit, in indoors we have temperature and relative humidity. Outdoors we have dry bulb temperature and humidity ratio. But the humidity ratio, it's not the same as the specific humidity. So that's why we have to look at the units. This is pounds divided by kilopounds, and this is in Revit, this is pounds divided by pounds. So we have to multiply this by 1,000. Okay, so I wish we had a tool in which everything would, but we don't have it. So that's why knowing all these parameters and concepts and units, especially units, it's important. Okay. So if we want to compare, first we have to make sure that the outdoor conditions, we are comparing the same outdoor conditions. If we are not doing that, it won't work. Then the next thing we have to do is to compare the R value. Okay, so that's why we had done this before. And here in the 3D view, we need to see the R value of the wall. So in this wall, we have 44 here. And in the, so yeah, I think we did this last week. This is 44 as well. So we have the same detail, kind of. But now we should type the same area of walls. So how can we get the area of the wall? Well, if we select the wall, we have the area. So you see that this wall is 294 square feet. Okay. So if we click on this wall, this is 71.74 square feet. Okay, we can type this. Let's do it. This wall is 294. This wall is 71. Again, I'm rounding up or down. This wall here is 76. And that wall there is 110. So this is 7, 7, 4, 11, 1, 2, 7, 9, 7, 6, 9, 25. 2, 4, 551 square feet. Okay, so what's the area of the wall? It's 551 square feet. Okay, so we can match first the outdoor and indoor conditions, indoor and outdoor temperature, indoor and outdoor relative humidity. Second, we can match the R value. And third, the square footage or the area of each element. Is there a way in Revit that we can do it? We can do that faster. I think we can. And I don't know if you have used schedules. Have you used schedules in Revit? Okay, so let's do it. I think it's in view. In view, here we have in this menu, we have schedules here. So if you click on schedules, we are going to do the first one, quantities. So in quantities, what do we want? So here we have a lot of things in. So let's say that we want walls. Okay, so we have the wall schedule. And what do we want? We want we want area. So we have to find area, double click. And what else? I need like some type or, okay, type, because we have different types of walls. And if we have different, because in this case, we have the same wall in all the, but in complicated buildings, we can have different walls. So we need the area and the wall type. And what else? In thermal resistance, well, maybe that's interesting. And width, volume, I think that's fine. Okay, so if we have this, we can click OK. And here we have, that's perfect, because here we have walls, we have exterior, interior, okay? And we have the storefront. The storefront, if we are considering storefront as glass, it's not a wall itself, because this is a curtain wall, okay? So that's good, because we have the thermal resistance, it's 44 in the exterior wall, it's 21 in the interior wall. We are not interested so far in the interior wall, only in the exterior. So the exterior wall, we have 110, 76, 72, well, 71, and 294, which is 300. Okay, well, probably this is more accurate, or no, it's the exterior is 295. Okay, so we have to look at the exterior walls. This is exterior, 295, 72, 76, and 110. Okay, so that's easier because we can create that schedule, and here we have all the information. And we are going to use the storefront. Okay, so I'm going to write it down because this is the wall. But here we have the curtain wall. So the curtain wall, I'm going to add curtain wall as glass, not as a opaque wall. So we have 197, 97, and 88. Okay, so this is 715, 2, 19, 28. Okay, so that's the total area of curtain walls. Be careful because curtain walls for Revit, they are walls, they are not windows. Okay, I think it makes more sense from the thermal point of view, considering curtain walls as windows, but for Revit, they are walls. So it's another type of wall here. Okay, we can create another schedule. If I go to view, I create another schedule, and now I want the category Windows. Okay, so in Windows, I think I did it wrong. Windows, now I have to select the area because this is what I want now. And I don't have areas for Windows. Boom. Again. Let's select, no, but this is own equipment. I want Windows. Okay. Okay, good. I don't have area. So that's comments, construction type. I'm going to use construction type, description. Height. Width. Come on. Solar heat gain coefficient. That makes sense. And no, I don't find area in this menu. If you find it, let me know, but I don't find it. So here we have 3 windows. Well, all the windows are 6 times 3, and the solar heat gain coefficient is 0.62. Okay, so according to this, I have 3 windows. Each window is 18 square feet because it's 6 by 3. So this is 54 square feet. So where can I insert in this Excel file the window information? Well, here you see that we have windows, okay? So for these windows, that's important because the orientation is important as well. So we need to understand the north, the south, the east, and the western windows. Okay, so we can have that schedule, but we need more information. So in this Revit file, this is the south elevation. So the south elevation, the area of the south elevation, it's 196. So this is the south elevation, and we have a window. Okay, so we can go to the south. So we have 196, the curtain wall plus 18 of the area of the window. In the west elevation, this is the west, we only have 1 curtain wall. So in the west elevation, the area of the curtain wall is 88. Let's go to the north elevation. We only have one window, so it's 18 square feet. And finally, in the east elevation, there's a curtain wall. So the curtain wall is 96 plus 18, which is the window. Okay, we have the curtain wall and the window. Okay, so now in this Excel file, I have to select the U value of the window. I have to select the area and the solar heat gain coefficient of the window. Let's start with the solar heat gain coefficients. It's always 0.64 because I haven't changed the solar heat gain coefficient in this window. So it's 0.64, 0.64, and 0.64. In all the orientations, the window is the same. Then the U value of the window. Okay, where can I find the U value of the window? If I select this and I edit type, I remember that we selected the same low emissivity triple glazing with the solar heating coefficient 0.65 or 0.64, but it doesn't matter. So this is the heat transfer coefficient. This is a U value. It's 0.256. Okay, so I'm going to type here 0.256 or 0.26. Well, that 0.26 and 0.26. Okay, so I have the same U value, the same solar heat gain coefficient for different orientations. And now I have a different area. So the area of the northern windows is 18. The area of the southern windows, it is 196 times plus 18. It's 214. The area of the east, it's 114. And the area of the western windows is 88. Okay. And why do we have different orientations? Because of the solar gains. Okay. For the thermal losses, the orientation doesn't matter, but the heat gains are important, and heat gains are important in summer. Okay. So for winter, if we're calculating winter loads or heating loads, we don't need different orientations. But if we are calculating solar gains, we do need different orientations. And where can we find that information? Okay, so that's a good of working with Revit or this kind of software in which all this weather data, they have a file with everything, with the temperatures, with the relative humidities, the solar irradiance. So they have everything. But here with this, we have to build what we are doing. Okay, so we need this information. If you see that Excel file, we have the white row here. So this is the row that we have to change. And the rows that are not white, these are not available for changing because we have operations here. It's about converting data because we have this in kilowatt hours per square meter. And then we have to turn this to BTUs, okay? Okay, so where can we find this? So we have another software, which is the PV Watts. PV Watts calculator. And in PV Watts calculator, again, it's a different software. We cannot create a building here. This is meant to calculate PV panels, but we can calculate solar irradiance outside the building. So this is what we need now. What we have to insert in this row is the solar irradiance this enter data for from PV watts. This is the energy that we have in the sun outside the window. So this is what we have to calculate now in different orientations. Okay, so how can we do that in PV watts? First, we need the same location, and the location it's in Revit. So in Revit, I think we change the location to Concord. Yes, so it was in Concord, New Hampshire. Okay, so now in PV watts, we can select here Concord, New Hampshire. Go and go to system info. Okay, so this is for, we are going to use this software to calculate the PV arrays. So the DC system size, the module type, the array, and the system losses, those are PV panel parameters. We're not going to use that so far, but we're going to use the tilt and the azimuth. So the tilt is the angle of the window, because now we're talking about windows with respect of the horizontal line. So if we have a wall, this tilt, it's always 90. If we had the skylight, then we will have to calculate the angle of that roof. But if we are just looking at walls, the angle, the tilt, it's always 90. And what about the azimuth? The azimuth is the orientation. So if we click here, info, north is 0, south is 180, east is 90, and west is 270. So if we are now with the north, let's type 0. Okay, so we are changing this. We are changing the tilt. It's 90 because it's a wall. And we are changing the azimuth. This is the orientation. It's 0 because it's north. And then we can go. Okay, so here we have these values. We have the solar radiation and the AC energy. The AC energy is the energy that we would produce if there was a PV panel with that orientation, but we're not calculating that. We want the solar radiation. And for the solar radiation, now we have to type these values on this Excel file. So in January, this is 0.64. In February, it's 0.82. In March is 1.26. In April, 0.96. May, 4, 5. And finally, December, 0.57. 0.56, sorry. Okay, it rounds up, so it's only one decimal, but it doesn't matter. Okay, so here we have the solar radiation outside the window in the month of January. So what does it mean? We have a wall, there's a window, and this is indoors. And this is outdoors. Here we have the sun. So the sun light and heat comes from the sun, millions of miles away from us, and this is our building. So in that building, we have a solar heat gain coefficient. Okay, so what does it matter if this solar heat gain coefficient is 0.6 or 0.65 or 0.64, whatever? That means that only 60% of the heat enters the building. So this is only 60% of if this is 100. So that's only 60% of the sun enters the building. And we have to multiply this times the area of the window. Okay, so this value is BTU hour per feet square. So this value is BTU hour, because we have multiplied this times the area of the window in square feet. Okay, so this is what we are doing here. We have the area of the window. We have the solar radiation outside the window. This is what we get with the 80 watts. And that's the area that enters the building. So it depends on the area of the window. That's the solar radiation that enters the building. It depends on the area of the window, and it depends on the solar heat gain coefficient. The solar heat gain coefficient is the amount of energy that enters the building. If it's 0.6, only 60% of the solar energy outside enters the building. Okay, so even in the north we don't have a direct radiation, but we have a diffuse radiation. So here we can see, if you look at this, you can see Paul walking, but then you can see the sunlight in the south, which is completely different than the sunlight in the north. Here we have diffuse light, and here we have direct light. So with the direct light, we actually see the sun. With the diffuse light, we don't see it. Okay, it's clear, it's light, but it's not direct sunlight. So that's why that even in the north, we have solar radiation. This diffuse radiation enters the building depending on the area of the window and depending on the solar heat gain coefficient. So we have done this for the north. We have to do the same thing for the, let's see, the south. So in the south, the tilt, it's always 90. The azimuth, if we look at this, the south is 180. So we have to type 180 and go to results. And now we have to type the results again. So it's 3.8, 4.1, 4.06, 2.8, 2.4. And finally, December 3.2. Okay. What about the east? Let's go back to this. Information east is 90. So here in the azimuth, I have to type 90. And then go to results again. And then type this 1.5, 2.1, 2.6. That would be 2.3. No, 2.75. In June, it's 3. July, 3.2. 2.8. 2.4. 1.8. 2. And 1.3 in December. So now we only have the west, and I think the west is 270, the angle. So I type 270. And I go back to results. And now I type all these values, 1.4, 1.9, 2, 3, 7, 8, and 1.2. Okay, so with this, I have this white row is the solar radiation outside. The problem is that PV watts works with international units. So that's why here we have first converting international units, kilowatts to BTU. And this row is the solar radiation times the solar heat gain coefficient. And the last one is the solar radiation times the solar heat gain coefficient times the area of the window. Okay, so what we have in this final row, in these results, it's the solar radiation in BTUs times the area of the window times the solar heat gain coefficient. Okay, so those are, this is the energy that we get from the windows or through the windows from the solar radiation. Okay, so with this, I am summarizing things. First, we calculate the wall with the width and the thermal conductivity. We get the R value. We calculate the area of the walls. We can do the same with the floors and the roof. Fine, then we have to look at the windows. So we have to calculate first the U value of the window and the solar heat gain coefficient. So those are parameters that are the same for every window. But the area, it depends on the orientation. Okay, so we have to calculate the area of northern, southern, eastern, and western windows. Then we have to calculate the solar radiation outside the window, and that comes from PV watts. So with this Excel file, we multiply the solar radiation outside the window times the area of the window times solar heat gain coefficient. And what else? There is more to this. So here we have ventilation. Okay. So when we have ventilation, remember that in Revit, we did this, but we worked with spaces. So in Revit, we calculated that space, and in that space, we had in space type, here we have the area per person. Then we had the air changes, no, the outdoor air per person, which is 20 CFM. Okay, so that's the ventilation or the ventilation parameters. What can we do here? Well, here first, we have the number of people, and then we have CFM per person. CFM per person, it's always 20. Okay, so by default, you can type 20, and most of the buildings have 20 CFM per person. But here we have to type the area of the number of people. So what's the number of people here? I think in Revit we have this information, because here we have people, we edit. We have said that it's 21 people per 20 square feet. Okay, so we select that space. Here we have 9.6 people, let's say 10. In this one, we have 4, so 14. In this one, we have 6, 20. And in this one, we have 6, okay, 26. So in this building, we have 26 people. So that's what we have to type here. Number of people, 26. Okay, so we have 26 people, 20 CFM per person. And here we have the formulas for the sensible heat and the latent heat. Well, that's important, but okay, I will explain later why we divide this between sensible and latent heat. What is important here is the heat recovery. Okay, so I think in systems, we talked about the heat recovery in the air handling unit, and we said that we can save a lot of money and a lot of energy by placing heat recoveries in buildings. And that's the efficiency. Okay, so the total ventilation load depends on the heat recovery. So far, we are going to type 0 because we don't know what Revit does in terms of heat recovery, and there is no way that we can know what Revit does. Okay, so here we have some uncertainties between these two and Revit. So let's type 0 by default, okay? And then we'll see what happens. And finally, we have infiltration. So for infiltration, so infiltration is complicated. What do we do in Revit infiltration? I think in space type, here in we have air changes per hour. We do have infiltration. Okay, so we have infiltration, airflow per area. So it's 0.04 CFM per square feet. Okay, so we have that value. This is the value that we have by default in this in Revit. The problem is that the infiltration, it's always in air changes per hour. Okay, so I will explain that later again, because here the infiltration, and that comes from ARCH360. We need to know the air changes per hour at 50 pascals to begin this number from the blower door test. Then that N value depends on the zone in which we are placing the building. And then we have to calculate the volume of the building, the interior volume of the building. So as you can see, that number according to the ARCH360 and that number according to Revit, they don't have anything, they are completely different. Okay, so I think I have to explain that in one lesson, but it's too much to explain it today. So this is what we have. Okay. So at the end of this green column that we have here is the sum of the heating loads through the walls, the heating loads through the floor, the heating loads through the roof, the heating loads through the window, and then we have ventilation, and then we have infiltration. Okay, so let's analyze this. So through the walls, in this case, we have the R value, we have the area, and through the walls, we have 900. If we go to the Revit report, and we have walls, well, here we have wall, and here we have the partition, Let's look at the envelope, okay? Because I rely on this number better. But here we take into account the infiltration. Yeah, so it's difficult to compare things here in the Revit report and in that one. Anyway, let me see the roof, because in the roof, what is the R value of the roof? It's 52. So what's the R value of the roof here? It's 72. So probably this is too much. I'm going to type here less thermal insulation. Okay, so now here I have an R value of 52. What's the area of the roof? I can check it here. If I select the roof, the area is 665. So I'm going to type here 665. And now we have 9,900 through the roof. In this Revit report, the roof, it's 600. In my case, it's 900. Okay, so those are similar values. What about the floor? So for the floor, the area of the floor is the same as the area of the roof. So it's going to be 665. And the R value of the floor, I think in Revit, it was around 20. Yeah, it's 26. Okay, so for the floor, I'm going to remove some of the thermal insulation here. Probably this one. Okay, so now it's 20. So now the numbers are similar in R value and area. And then we have this. Okay, so we have these values. So through the envelope, we have 12,000. If we are adding up the values through the floor, wall, roof, and windows, the total value is 12,000. Here in Revit is 10,000 through the envelope. Okay, it's not that far. The thing is, through the ventilation, I have 1,300. So considering that the occupancy that we have fixed here, my ventilation is 61, so it doesn't make sense. That means that here probably I have a heat recovery. So if I have a 90% heat recovery, which is possible, here we can have 6,000. Probably the heat recovery, it's a 95, 3,000. Okay, so it's clear that Revit has considered a very good heat recovery. So basically, because through the ventilation, we have 1,000 here, but I have to add up all the offices. So this is 8,000. Okay, so that's important. So for ventilation, I have 8,000 in that space. In office 4, I have 8,000. In office 1, there is 6,000. And finally, in the meeting room, there is only 1,000. Okay, so the total ventilation load is 16, 24, 25,000. So the heat recovery If this has to be 25,000, the heat recovery can be 70%, 65%. Yeah, so that makes sense. Around 60%. Okay, so that makes much more sense. So here we have considered a 60% heat recovery, which is, yep.
Is there a way to make that
It's not standard. In Revit, we have to specify the heating and cooling system. But in spaces, if we select this, the condition type is heated and cooled. Okay, so that's it. The space type, the electric loads, design heating. So here we don't have a way to specify the system. So Revit does something. So it considers a 60% heat recovery, I think, because it's something, it's common sense. Can we specify that? In Analyze, there's another way to specify this, which is the energy settings. So in energy settings, I haven't touched this. So I have used the default values, okay? But here in advanced options, I can specify the building service, the building infiltration, and different things here. Okay, so here the building service, this is what Revit has considered, a variable air volume system with a single duct. But there is no way I can't specify this heat recovery. So Revit has these options, and it has a lot of options. Okay, but we don't know what it does. That's a problem with Revit. So I can figure out what it does, because if we have the same occupancy, the same indoor and outdoor conditions, and the formulas to calculate the sensible and latent heat are these, because Revit, this is what ARCH360 says. So I can understand that Revit has used a 60% heat recovery. Okay, but this is something that in Revit is not clear. In other software, you can specify, okay, with or without heat recovery, that efficiency. I can specify more things. In Revit, I can select different systems, but I don't know what's within those systems, okay? So yes, we have limitations. So at the end, we have to figure out that things are going well. So through the envelope, Revit says that we have around whatever, and this is what I have here for the ventilation. I have numbers, and then for infiltration, we can see what Revit says about infiltration in the report. If we go to the report, here we have infiltration. Okay, so when it comes to infiltration, I have 1,000 or 1,300 in that space. It's 1,300 in that space too. In that space is 2,300. And in that space is 1,700. How much is this? So okay, so it's around 6,600 BTUs per infiltration. So what do we have here in infiltration? 3,000. It has to be double. So we can double this number. And now it's around 6,000. Okay, but again, how does Revit calculate the infiltration? We have done this. So in Revit, we can go to the space And in buildings, in space type, I can type here the infiltration per area. But I don't like this because we're going to look at what ARCH360 says about infiltration. And we should, ARCH360 uses this parameter. Okay, so we have to carry out a blower door test, because without the blower door test, we don't know the infiltration. Okay, so it's impossible. In this building, what's the infiltration in this building? I don't know. I have to do that test because it's not something calculated, because it depends on how it is. If there are cracks between the walls and the windows, the infiltration will be terrible. If the construction is perfect, the infiltration will be very low. But we can't calculate that. We have to test it in the real building. Okay, so Revit has taken into account that infiltration. So that infiltration means that the air changes per hour at 50 pascals when we are carrying out the blower door test is 4. So that's what it means. Okay. So that's it. So now we have numbers that are similar. We have the same kind of heating loads through the envelope. We have the same load for the ventilation, and we have the same load for the infiltration. So, so for the ventilation, I agree, because I have typed the same number of people in Revit, and in this Excel file, I know that the CFM per person, it's 20, that's good. And considering 60% of heat recovery, we get the same value. Perfect, okay? Because this is what usually happens. When we have to calculate ventilation loads, it depends on the number of people, and it depends on the heat recovery. So a 60% heat recovery, it's something that it's usual in most of the buildings. Okay, so I can say this. When it comes to the infiltration, I have to check for, look at Revit. If we go to the energy settings, the advanced energy settings, in infiltration class, when we have different options. By default, it's none. But if we click here, we have loose, medium, and tight. None is the default. It doesn't mean that there is no infiltration, because there's some infiltration some way. But we have loose construction, medium construction, or tight construction. Tight is better. Tight in terms of ACH 50, it's less than 0.6, I think. So it's very good. Loose, it would be above 3 or 4. So this is what we have done. So I think when you select none, you have like a loose infiltration. So it's not very high quality. It's not a high quality building. Okay. But again, we haven't touched this. We have said none. So that means that this is the default infiltration. Okay. So now we have 2 tools that are giving kind of the same values, but I like this tool because, well, I like it. It's complicated, but at least I can control what I have done. I can control the heating loads through the windows. I can control the heating loads through the walls. I can control the infiltration and ventilation. With Revit, I have this report, period. Okay. If I rely in those results, perfect. But I don't know what Revit is doing. So to understand what Revit is doing, that's why I'm using this, but it takes time. Okay, so I have to type all these with my hands. I have to go to PV watts to calculate the solar radiation. So I don't mean it's easy. It's not. But what I'm trying to do is to understand what Revit is doing. So now I think I understand what Revit is doing, because I'm typed the same R values for walls, floors, and roofs. I have the same outdoor conditions. I have the same areas for walls, roofs, windows. I have the same, or I have calculated the U value and the solar heat gain coefficient in the area of windows, the same values as in Revit. I tried to understand the ventilation and the infiltration. So now I have an idea of what Revit is considering. And the numbers are quite similar. Okay. But that's all I can do. Okay, so it's not, I don't know if the thermal loads through the envelope, it's 12,000 or 11,000. I don't know. And I don't mind. So I don't know if the ventilation it's 24,643 or the Revit 25,000. I don't mind. They are similar, and this is what really matters. Okay, so if I can get similar results with two different software tools, well, I'm on my way to understand what's going on. But am I happy with this? No, I'm never happy, because I want to try a third tool. Okay, so I'm trying Revit. I'm trying, let's say that this is a Keene State College tool, this Excel file. And I want to try something different. I'm going to try the MIT tool Design Advisor. I think I asked you what, if you ever heard of MIT. Do you remember what MIT stands for? What? Yes, MIT. There you go. It's the Massachusetts Institute of Technology. Probably this is the most prestigious technical school in the world. I mean, for architecture and engineering. We're going to use that tool, and this tool comes from the Massachusetts Institute of Technology. It's an online free tool, so you can use it. So they have developed, in theory, teachers and students, they have developed this tool to calculate the same thing that we are doing here. Okay, so we are going to calculate thermal loads in a building. So that's the third. So I have Revit, I have the Keene State College tool, that Excel file, and I have the MIT Design Advisor tool. Okay, so how does it work? I have to go to Setup, and I have this interface. Can we model a 3D building here? We can't. Okay, so it's in this case, it's the same as this tool here. We can't create a 3D model and run the simulation. We have to type indoor and outdoor conditions. We have to type areas and all that stuff. Okay, so that's the first thing. Region. Can I select a region? I can select the region in USA. Can I select a city? Can I select Concord, New Hampshire? No. For those MIT guys, I think New Hampshire doesn't exist. Good. So what is the closest? Boston. Yeah, I would say Boston. Okay. So that's the first limitation. We can't select, and we can't type the outdoor conditions. So I have to select Boston. Okay, it's close to Concord. So and then occupancy and equipment. Okay, choose an occupancy type or select options manually. Person density. Well, that's interesting. That comes from the Massachusetts Institute of Technology, and the default units are international units. Is there a way to change these units to imperial units? No, that I know of. Okay. So that's the, here we have questions, answers. Where can I find the list of the model assumptions? We're going to get a copy to phones. We're going to source. We can research. Okay, so here we have like the instructions, but we can't change the units. Let's look at introduction. Top right. Oh, IP units. Good. Okay, perfect. So yes, I changed this, but does it work? You changed yours? Yeah, not like all. But here we have people per square meter. And okay, so here we have Fahrenheit at least. But well, we have people per square meter. We don't have people per square feet. Okay, so the first thing we need to know in Revit, I think we have in the spaces, in building, there is like, okay, 20. Here we have area per person. Here we have, they are asking people per square feet. Okay, so here we have 20 square feet per person. This is Revit. 20 square feet per person. Okay. Yes, area per person. In this MIT tool, we have people per square meter. So what's the area of this? I can select the floor. So that's the floor area. And it's 660 square feet. So we have 660 square feet. And here we have 20 feet per person. Okay, so if I divide this by 20 square feet per person, what I have here, it's 33 people. This is what I think, I calculated this in a different way, and it was around, yes, I did it here. So what was the number of people? 26. And according to this is 33. Okay, so let's say 30, doesn't matter. So we have 30 people. But now in this tool, they are asking me the persons per square feet. So if I have 30 people, no, they're asking me people per square meter. So what is the square meters of 660 square feet? So I have to go to square feet to square meter calculation. So 660, it's 61. Yeah, it's divided by 10. So this is a 30 person in 61 square meters. So it's around 0.5. Okay, so in my design advisor, here I have to type 0.5 people per square meter. Okay, I'm sorry, it's not my fault. I wish there was a tool in which we could do this easily, but look at this. They are asking for the same information. They can ask us the number of people or square feet per person or a person per square meters. It's always the same value, but they are asking this in different units. Okay, so that's why we have to master this, because we don't know in our company. Yes.
I think you've said this before, but what are the 4 different scenarios? You have different
Yeah, the scenarios is that I can change different things. I can change the system, I can change the U values, and then I can compare how the system improves if I add more thermal insulation. So I can do it up to 4 times, okay? It's useful. Okay, so we have person density. Here we have lighting. In lux, we haven't talked about this. Lux is the power or the energy of the lamps, okay? And then the equipment. And we have watts per square meter. I'm sure that in Revit, we have done this. If we go to Revit spaces and we go to space type, here we have a lighting schedule. Here we have a power schedule. Okay, so we have a lighting load density in watts per square feet, and we have power load density in watts per square feet. You see? Okay, so the lighting load density and the power load density is the same thing they are asking us here. So does it make sense? 400 lux. Yep, but there's a conversion between watts per square meter or square feet and lux. We're not going to talk about it. Anyway, as you can see, these values are here, but in different units. We can rely on default parameters because in buildings, the lux is the level of light, artificial light that we need in a building. So I assume that everywhere in the world, we are using the same kind of light because we are working in an office or in a, so we can rely on that. And then the power load density is the number of computers, the number of devices that we have there. Okay, so I haven't changed that here, and I'm not going to change this in the design advisor. But again, we have different units. So they are asking for the same parameter, but in different units. Okay, the ventilation system, good. One of the things that they make perfectly clear in these questions is, where can I find a list of the model assumptions? If we type here ventilation, or heat recovery, I don't know, but oh, so there is an assumptions page. Okay, so here weather data, ventilation, the changes per hour, when is equivalent to replace fresh air. The model does not directly predict infiltration rates, and fresh air is brought to the building. No energy is recovered from the exhaust air. Okay, so yeah, we have to read this. It's very tiny. They don't assume heat recoveries, so they don't consider heat recoveries. Okay, so those guys in the MIT, they don't have this simple percentage. Okay, what is the heat recovery system? A 60%? They don't have this. They don't assume that we can have a heat recovery in our building. Okay, so when it comes to the mechanical cooling and heating, we can have mechanical ventilation or natural ventilation. We can assume mechanical, but without the heat recovery. So we can specify the indoor temperature. So the indoor temperature, we have specified 70, the maximum and the minimum. So let's say 71 and 69. So the average would be 70. Okay. So the maximum and minimum means that if we are above 71, the system stops working. And if we are below 69, the system works again. Okay, so that the temperature is always kept between 69 and 70. What is the maximum relative humidity? 60, I think is too much. We're going to say 50. Okay. And then the ventilation rate. Again, I have changed the IP units, but here we still have liters per second or air changes per hour. So here we have 15 liters per second. Well, I know those units, 15 liters per second, it's around 20 CFM per square feet. Okay, so we can keep 50, and then the air changes per hour. Well, it's the same. Okay, so 15 liters per second is the same as 9 air changes per hour. But I have done this before, so 15 liters per second is the same as 20 CFM per person. Okay, the thermal mass, high mass or low mass. That's important, and it's something that we can't do here. So here we have information about the materials, but we don't take into account the thermal mass, which is relevant. Okay. So do we have concrete, or I think we had the roof. If we edit type, if we have concrete, and we do have concrete, we have 1 foot, this is high thermal mass. Okay, so when we have concrete slabs or roofs, we have a high thermal mass. Building geometry. So here we can select either one facade or 4 facades. Well mixed air between zones or unmixed air between zones. Okay, I don't mind, but it's we have 4 facades because we have a detached building. If we have an attached building, then we have only 1 facade exposed. But here we can select 4 facades. And the building orientation, it's north, south, east, west, east, west, kind of. And the building dimensions, here we have feet. So instead of the area, we can calculate the size. So I have to go to annotate. So this is around 31 by 20. Okay. So this is 31 by 20. Room dimensions, typical room properties. Okay, so here we have typical room dimension. What does it mean? Well, here we have 3 rooms or 4 rooms. What's the typical dimension? This is slightly smaller, this is slightly bigger. So I would say that the typical dimension is this one. Okay, so I'm going to type this dimension. It's 14 by 10. Okay, so let's do this. 14 feet. The depth is 10. And the height, I have to go to the section. So the height is 10 feet. It's 9.8. Okay, let's say 10 feet. Window primary facade orientation. Where do we have the most glass? I would say south, because in this, I think the southern facade is the one with the largest area. So I would say, well, probably it's this is south, this is east. So I would say southeast. Southeast. Now, window area of exterior wall. What's the percentage of the area? I think we had here the area of windows. It's 382. And here we have the area of walls. Okay, so the percentage of the ratio window to wall area is 382 divided by the wall, which is 551 times 100. So it's 69. Okay, so the window to wall area, it's around 69%. We have a lot of window area in this building, okay, compared to the area of the walls, we have a lot of glass. And now select a window type. Here we have triple glazed. We do have triple glazed. Glass type, I think we have one low emissivity coating. Let's select high performance and low emissivity coating because, okay, so let's select the best glass available. We don't have any overhang. Wall description. What is the R value of the wall in square meter? Oh, there. So we have the R value, but not in the imperial units. So we have to change these units too. So we have to convert units from our square feet Fahrenheit divided by BTU to square meter Celsius divided by watts. Heat transfer coefficient converter. Okay, so let's do it with the heat transfer coefficient to watt meter Celsius. Okay, the heat transfer coefficient of the wall is 0.02. So this is 0.11. So 1 divided by 0.11, it's a 9 point. Okay. So this is going to be 9. Okay, perfect timing. We have 1 minute left. So we have to a region and the city. What the hell? Oh, the region, it was USA. The city, it was Boston. So let's click and see what happens.